Welcome to today's Explainer. I am seriously excited to share this one with you because we are tackling a really fascinating topic. We're going to look at how our everyday electronics take incredibly weak, tiny signals, like a faint whisper into a microphone, and somehow boost them into powerful outputs that can literally shake a room. We are exploring the world of multistage transistor amplifiers. And the absolute best part? We are going to do this completely conceptually. That means we're focusing purely on the brilliant engineering logic, skipping all the heavy math and calculations, and just enjoying the elegant journey of a signal. So, you might be wondering, and it's a great question to start us off, if the whole job of an amplifier is to make a signal louder, why on earth do our devices need 3, 4, or even 6 of them working together? Why not just build one massive super strong amplifier and call it a day? Well, as it turns out, a single stage of amplification is almost never enough to drive a practical output device, like a loudspeaker. A single transistor simply cannot do all that heavy lifting on its own. Okay, let's take a quick look at our roadmap for today. We're going to cover why one amplifier isn't enough, how capacitors act like traffic hops, the concepts of gain and bandwidth, and then we'll dive into RC and transformer coupling, direct coupling, and finally, choosing the right connection. Let's get right into it. Section 1. Why one isn't enough. Like we just established, a single transistor's output is just too weak to take a tiny radio wave and turn it into booming music. So engineers solve this weak signal problem through teamwork, which is a process formally known as cascading. By connecting multiple amplifier stages in a series, the output of the first one becomes the input of the next. It's kind of like passing a baton in a high-speed relay race. Just follow the journey of the signal here. We start with a really weak input on the left. It enters the first stage, gets a little boost, travels through a coupling block, enters the second stage for another boost, and eventually emerges as a powerful output. Now those coupling blocks right in the middle, those are absolutely crucial, which brings us perfectly to our next topic. Section 2. Capacitors, the traffic cops. You see, you can't just wire transistors directly to each other willy-nilly. If you do, their internal power levels will completely mess with each other and ruin the baseline of the whole setup. Enter the capacitor. Think of a capacitor like a bouncer at a very exclusive club. This bouncer firmly blocks the steady, boring direct current, the DC power, from sneaking between stages. But they gladly open up the velvet rope for the fluctuating alternating current, which is our actual audio signal. Because of this, when we're analyzing the audio's journey, we can basically just imagine these capacitors as straight pieces of wire keeping the signal moving. Now, you'll generally spot capacitors playing two distinct roles in the circuit toolbox. First, we have coupling capacitors. Just like we talked about, these sit between the stages to pass the signal baton forward while blocking that DC bias. Then you have bypass capacitors. These guys act like a VIP fast-track lane within a single stage. They provide a super low resistance shortcut for our AC signal to go right around certain internal components. This prevents any gain loss and preserves all that precious signal strength we worked so hard to build. Section 3. Key concepts, gain and bandwidth. So our amplifiers are safely talking to each other, but how do we actually measure their success? Let's start with gain. Gain is simply the total boost of the signal. When you cascade stages together, their individual gains actually multiply. But to keep things intuitive, engineers express this massive multiplication in decibels. Why? Because human hearing actually responds logarithmically to loudness. Our ears hear in doubling effects, not absolute linear math. It's a pretty elegant way to measure things. And that brings us to our second key concept, bandwidth. Think about the middle section of a bell curve, right between the lower and upper cutoffs. That right there is the sweet spot. When we amplify a signal, we want a nice uniform gain across those specific frequencies, so the output sounds perfectly natural to the human ear. If a frequency falls outside of this sweet spot, the sound gets heavily distorted, and nobody wants to listen to that. Section 4. RC and transformer coupling. Let's look at the actual flavors engineers use to link these stages together to hit that sweet spot. First up is RC, which stands for resistor capacitor coupling. When you map this out, you get a beautiful, wide, flat plateau in the middle of the frequency response graph. That flat shape means that for mid-frequencies, which covers almost all human speech and music, every single note gets amplified perfectly equally. That is how you get crystal clear, high-fidelity sound. Because of that beautifully consistent curve, RC coupling brings some massive pros to the table. It delivers excellent audio fidelity, and since resistors and capacitors are tiny and cheap, these setups are incredibly compact and cost-effective. They're absolutely perfect for the early stages of a public address system where you just need a solid boost in voltage. But there is a catch. They offer really low raw power gain, and they are notoriously bad at something called impedance matching. Basically, that means while they make a signal's voltage larger, they seriously struggle to push that raw power into a heavy load, like a giant speaker. So what's an engineer to do when they actually need to push real power into a heavy speaker? They bring in the heavy lifters, transformers. But look at the trade-off. Instead of a nice flat plateau, the performance curve for a transformer is bumpy and humped. A transformer's performance jumps all over the place depending on the frequency. It's visually obvious why transformers can easily distort complex, layered sounds like music if you use them in the wrong spot. Basically, the pros and cons of transformers are the exact opposite of RC circuits. Like I said, they are the heavy lifters. Their absolute biggest advantage is excellent impedance matching. This means they can efficiently transfer maximum power directly into a demanding output device, like a loudspeaker. Plus, they don't lose signal power as heat the way resistors do. The downside? Well, we just saw that poor frequency response. Plus, physical transformers are bulky and expensive. Because of all this, engineers typically save transformers strictly for the final power stage, right before the speaker. Section 5. Direct coupling. Now, what happens in a unique scenario where neither capacitors nor transformers will get the job done? Enter direct coupling. What's really interesting here is what's completely missing from the circuit layout. There are no coupling capacitors acting as bouncers, and absolutely no bulky transformers. The output of the first transistor is literally wired straight into the input of the second. Simple, right? But wait, didn't we establish earlier that direct wiring messes with the DC power baseline? Yes, so why do it? Because sometimes you just don't have a choice. Direct coupling is the undisputed master of amplifying extremely low frequencies. We're talking signals that fluctuate so incredibly slowly they're almost at 0 hertz. If you tried to use standard capacitors for ultra-slow signals like those from a thermometer or a light sensor, the physical capacitors would have to be unbelievably, unrealistically huge. So for those delicate, creeping signals, wiring them directly while using clever complementary transistors to balance things out is quite literally the only way to boost them. Section 6. Choosing the right connection. Ultimately, engineering is all about picking the right tool for the job. You can look at a summary matrix and see exactly how an engineer balances those real-world needs without having to do a single calculation. Do you need clear audio, low cost, and a small footprint? You go with RC. Do you need to drive heavy, raw power to a big speaker? You accept the bulk and the cost and you use a transformer. What if you're dealing with extremely low frequency signals in a tight space? Direct coupling is your absolute best friend. Listen, if you take absolutely nothing else away from this explainer, let it be this golden rule of multi-stage amplifiers. For pure voltage and crystal clear audio fidelity in those early stages, use RC. For the final, heavy power punch at the very end, use transformers. And for the absolute lowest of frequencies, you wire it direct. It is such a brilliant, elegant system of teamwork. I want to leave you with a thought before we wrap up today. We know what works incredibly well right now, but think about this. As our everyday devices like smartwatches and those tiny wireless earbuds become microscopically small while still demanding even higher audio fidelity and power, how will engineers continue to evolve and balance these physical coupling methods? It is a truly fascinating challenge at the absolute frontier of electronics. Thank you so much for joining me on this journey through the circuit board today. Keep wondering, keep learning, and I'll catch you in the next explainer.